Another type of algorithms operates always on blocks of specified length. For example, it always encrypts 56-bit or 128-bit blocks. This type is called block ciphers. Most symmetric ciphers belong to the block type. They are more secure than, and just as efficient as, stream ciphers. Many symmetric block ciphers follow the same structure and utilize the same method for repeating operations, rounds. They use Feistel's network. The architecture of this network can be seen in the schema below. Since the network is based on an assumption that the plaintext has a fixed length, you need to split it into blocks first. While it's good that the cipher encodes 128 bits, an email that you want to encode is shorter than that size. You need to split the email in some way into 128-bit blocks. The transformation method depends on the block's cipher mode of operation, which will be covered later. Why is Feistel's network so popular? Its structure relies on dividing the plaintext block into halves and then performing a function f on one part of the plaintext. The output will be combined with the other part of the plaintext and their positions will be switched, left into right, right into left. We switch the message into blocks. You know already that block ciphers operate on message blocks of specified length. When one part is transformed by the function f, this is the encryption, we connect the encryption result with the remaining part. Next, the two parts switch positions and the operation is repeated. What makes this solution so simple and popular? This method works with any f function, even if the function is irreversible. A message is split into two halves and one part is encoded. What's crucial here is that a round key is used for the encryption. If you flip the order of the two parts and go back to the start, the internal key will be different. The key will be the second round's key. The calculated encrypted result is combined using the XOR function. This again gives us two halves. Decryption is parallel, which means the operation is symmetric. It's again enough to divide the plaintext into two parts and perform the function f on one half using a round key. The output then should be XOR'd and repeated in as many rounds as required. This solution doesn't guarantee security. It's simply a mechanism, a mode of operation, or a transformation method. The security, as such, is only provided by the function f. It has critical importance in the structure. So what should you introduce into this network? The function has to mix bits to achieve a nonlinear relationship between the ciphertext and the plaintext message. This is the most crucial and the hardest part. The image above shows substitution tables, S-boxes. They are actually the substitution tables used in the DES algorithm. The algorithm will be covered at length in a moment, but let's flesh out this example now when talking about mixing. How can a nonlinear relationship be discovered? Note that if you take a look at the values at the intersection of columns and rows, it's difficult to see why 8 should be at the intersection of the second row and third column, or why 12 is at the intersection of the third row and first column. The relationship is nonlinear. If you submitted row and column numbers and looked up the values in the cells, this would be a nonlinear relationship between the plaintext used to generate coordinates and the ciphertext, the output that's at the intersection. Substitution tables are used in almost all symmetric key block ciphers. It would be helpful if our function f performed bit permutation or flipped bits. It could be used to obscure some relationships. The function should also exhibit the avalanche effect so that the change of a small amount of plaintext bits, ideally 1 bit, would be demonstrated in the significant change of as many ciphertext bits as possible. Ideally, all bits should change. This can provide the cryptographic system with some immunity to a certain category of attacks, to attacks that manipulate the plaintext. If an attacker can provide any input into a system, they're able to observe how encryption is applied and draw some conclusions. If you maximize the diffusion, the attack will be much harder to pull off. The function f must also provide compression to let the Feistel round operate. The final ciphertext has to be as long as the initial plaintext.